Welcome back, everyone. In this video, I'll be going over the lecture for hyperbolic trig functions. Now, in this section, we will talk about what the hyperbolic trig functions are. I have trig written in parentheses because even though they have the names of trig functions, they're usually just called the hyperbolic functions. But their properties are so similar to trig functions that very often, and even the way they're named is after trig functions. So they are called hyperbolic trig functions, but if you hear me say just hyperbolic functions, it means the same thing. All right, so we'll start with the definition, and then we'll talk about actually evaluating these hyperbolic trig functions, and then we'll finish up by talking about the derivative formulas for the hyperbolic trig functions and actually using them. All right, so the hyperbolic trig functions get their name because in a way they're sort of similar in how they're defined. Trig functions, regular trig functions like sine and cosine, and then the other four we get from its definition come from the unit circle x squared plus y squared equals 1. And in a trig course, you spend a long time talking about angles and how sine and cosine of theta and all these reference angles, their periods, all this stuff. Well, the hyperbolic trig functions or hyperbolic functions get their properties from what's called the unit hyperbola. It's almost the same equation. It's negative x squared plus y squared. Just realize it's not very readable. Negative x squared plus y squared equals 1. Now, if you remember things about hyperbolas, like circles, are basically what's called 2 to 1, meaning if you draw a vertical line through the graph, it's going to hit it twice. So really, this hyperbola, which I'm going to show you on Desmos in just a second, has a top half and a bottom half. But when we talk about the hyperbolic trig functions, we're just going to be referring to the top half. Now, we don't really need to deeply understand that. I just wanted to mention that in case someone was familiar or remembered about the hyperbolic functions or hyperbolas. So I'm going to go ahead and just graph this. Negative x raised to the 2 plus y raised to the 2 equals 1. And the hyperbola, like I mentioned, it's pretty hard to freehand. It's not like a circle because it sort of looks like a parabola in that it has this sort of U shape at the bottom, but the farther you get away, it sort of just looks like a line. And if you remember things from like a pre-calculus type of class where you talked about conic sections, you know this is called a slant asymptote, but we don't need to get into all that. The idea here is that if you follow along with the x value, that's actually what's called the hyperbolic sine function, which we abbreviate sine with an h, so sin, and then an h after it. And if you look at the y value, that is the hyperbolic cosine, and that's why I have it labeled right here. Right. And once again, this is not a trig course. We're not going to talk about anywhere near the depth of material of hyperbolic trig functions as regular trig functions. Just wanted to talk about where these names come from. Now, what's interesting is that because the hyperbola doesn't go around in a circle, it doesn't repeat itself, hyperbolic functions are very different in how they work. But the cool thing is that, like I said at the beginning, a lot of their properties, a lot of their formulas, a lot of their rules are so similar to the way regular trig functions work that they're really just given this name for convenience. All right, so below I have the actual formulas. If you're talking about the hyperbolic cosine function, hyperbolic sine function, and so on, you actually can derive a formula for them. And it's in terms of exponential functions. And what I'll do is I'll also graph the sine and cosine just so you, or I should say hyperbolic sine and hyperbolic cosine just so you can see that. But the definition of hyperbolic cosine of x equals e to the x plus e to the negative x over 2. That's its definition. It comes from the hyperbola, but if you work out the y value, if you trace the y value, it actually will trace the same values here. And the x value, hyperbolic sine, actually follows this shape. Hyperbolic sine of x equals e to the x minus e to the negative x over 2. And then, not coincidentally, the other four hyperbolic functions are defined exactly the same as the regular trig functions in terms of hyperbolic sine and cosine. So hyperbolic tangent of x equals hyperbolic sine of x over hyperbolic cosine of x. Hyperbolic cotangent of x, which looks like coth of x, equals 1 over hyperbolic tangent of x. Hyperbolic secant of x, notice that the only pattern is that we have all the trig functions are the first 3 letters and then we're putting an h. The hyperbolic secant function is 1 over the hyperbolic cosine of function, and the hyperbolic cosecant function is 1 over the hyperbolic sine function. So you should be familiar. We've talked about all of these in the class as trig functions anyway, but you should remember from trig, if you knock the h off all these formulas match exactly the same. Now what I want to go ahead and do is look at the graph of hyperbolic cosine and hyperbolic sine. So what I'm going to do is graph. You can actually type in Desmos, hyperbolic cosine, hyperbolic sine. But what I want to do is, this is hyperbolic cosine. It's cosh of x. Notice it sort of looks like a parabola. It traces the y value of that hyperbola. So the lowest it goes is 1, as we can see. But what happens if you graph the definition? Well, y equals e raised to the x plus e raised to the negative x. Oops. You can already see there it's kind of the same shape. And if you divide it by 2, it is exactly the same shape. All right, we've seen examples with Desmos that when you graph 2 graphs on top of each other, it just has to take one color. But if I click on the other one, the blue goes right on top of the green. So that is its definition. If you switch to sine, so hyperbolic sine of x sort of looks like x cubed, if you know that off the top of your head. And all that's going on here is this plus gets switched to a minus, but it gets perfectly overlapped. The blue and the green are on top of each other. Now, one thing I had mentioned is that hyperbolic sine is the x value. Notice the x values go from negative infinity to infinity here. Well, what's happening to this graph is it's taking on values down from negative infinity up to positive infinity. And if I go back to the cosh, hyperbolic cosine of x, some people say cosh, the y values here only range from 1 up to infinity, and that's exactly what the y values do here. Now, once again, can't repeat it enough. You don't need to know a lot of details. What's going to be interesting, why we even talk about hyperbolic sine, hyperbolic cosine, and the rest of these, is really because when you look at things happening naturally, one of the prime examples is if you have a bridge and it's suspended by 2 points, so it sort of makes this shape. You have a suspension bridge, it's held up at these 2 ends and it's just sort of allowed to dip down naturally. The shape of that is hyperbolic cosine in some way. So it does occur naturally. It's not just a random thing to get you to try to learn more formulas. But let me go ahead and erase that. All right, so what I'm going to do first, before we do anything else, is we need to actually talk about evaluating hyperbolic trig functions, because basically most calculators are not going to have buttons for these on them. And if you're using a handheld calculator, you need to know how to evaluate them. Well, the thing is, you evaluate them directly from their definition. And I'll show you in the calculator as well, because a lot of times, depending on the number you're plugging in, you're going to have to use a calculator to round. But what you should do, just going forward, is remember the definition of hyperbolic cosine, hyperbolic sine. Cosine is the one with the plus, sine is the one with the minus. Otherwise, they're exactly the same. And then remember the other 4 are defined in the same exact way as the regular trig functions. All right, so let's say you have to do this, and we want to figure out hyperbolic cosine of the natural log of 4. Now, naturally, you might be looking at this one and could think, why is he asking us this one first? This seems more complicated than the other ones. Well, it's because the way its definition is, if you have natural logs, it actually simplifies quite a bit. Because this is saying, take our formula for a hyperbolic cosine and plug in x is this. So for a hyperbolic cosine, we have e to the x, e to the natural log of 4, plus e to the negative x, e to the negative natural log of 4, and then all over 2. Now, it's possible to do this completely by hand because the natural log and e in this format, e to the natural log of something, cancel out. in order to completely simplify, you have to bring this negative sign inside as the power. So in one of the previous sections, we talked about doing the logarithmic differentiation. We used some log rules and we brought exponents out front. Well, here we're going to reverse it. So this negative sign, which is really -1, we're going to bring inside. And this is just good practice with log and exponent rules. We have e to the ln of 4 power plus e to the natural log. This would be 4 to the -1 power. And you can stop there and then go ahead and use your log rule to simplify. But 4 to the -1, if we're going to evaluate this at the end, we should probably go ahead and take care of that negative power. This is going to be 1/4. And we know negative exponents we can make positive if we bring the inside, or what's being raised to the exponent, to the bottom. So this is e to the ln of 4 plus e to the ln of 1/4. Right, and that's probably the main steps, because now if you remember how to simplify with e in the natural log, you're good. E to the natural log of something just cancels out and you're left with just the something. So in the numerator, we are left with 4 plus 1/4 all over 2. And now how can you completely simplify this? Well, we just have a fraction here, so it's just a number. If you multiply the top by 4, that'll get rid of our denominator here. We have to distribute the 4 through, we know that. And we just need to multiply the bottom by 4 as well to keep it balanced. So when we do that, 4 times 4 is 16, plus 4 times, when we multiply here, we'll get 1. So 4 times 4 was 16, plus 1 is 17, over 2 times 4 is 8. And you get 17/8. Now, Wolfram alpha can pretty much take in anything, which means if you just type in hyperbolic cosine COSH of the natural log of 4, it's going to give you a decimal usually, but if you hit enter, you can see that it's the same fraction, 17/8. All right, now what happens if you don't have the ln? Well, let's just plug it in. So the part B here, we have the same exact hyperbolic function, hyperbolic cosine, but instead of doing ln of 4, we just have 4. So we got e to the 4 plus e to the -4, right? Because it's e to the x plus e to the -x over 2. Well, this is one where if you weren't supposed to round any further, you would just be done, because e to the 4, very messy number, nothing's going to simplify. E to the -4, same thing. And the way you would do it in a calculator that doesn't have these hyperbolic sine and cosine functions is just, you'd have to type this in. So we'd have e raised to the e raised to 4 plus e raised to the, -4. Now, whenever it comes to anything in an exponent that's not just a whole number, even if it's negative, I put it in parentheses. So you see that. Then I divide it by 2. And you can double check, make sure it's reading it correctly. It does write it slightly differently, but e to the -4 is 1/e to the 4. And then the 1/2 is just from the 2 in the bottom. So it's reading it correctly. And rounded to 5 spots, we got 27.30823. And that's the best we can do. We got 27.30823. Now, of course, you can just type in hyperbolic cosine COSH of 4, and it'll give it to you in this. But the point is, not all calculators have this function, which means you can't do anything but type it in from its definition. Right. Oh, and I should also say, if you're concerned about radians versus degrees, because this has nothing to do with an angle, there is no idea of radians versus degrees. That's just for regular trig functions. All right, hyperbolic tangent, evaluate at 0. Well, we want, by its definition, it's hyperbolic sine of 0 over hyperbolic cosine of 0. Oops, I was about to write x. We want 0 there. All right, that's by definition, and now we can use the definitions to evaluate. It could take quite a bit of space just because we have to write down the formula, but for hyperbolic sine, it's e to the x, so it's e to the 0 minus e to the -x, e to the -0 over 2. And then hyperbolic cosine, we know that's e to the x, e to the 0 plus e to the negative x, e to the negative 0 over 2. And if you're looking at this kind of funny, it's probably because of the negative 0. I was just plugging in directly, but we know negative 0 is just 0. Well, typically with this, I would say make sure you simplify first, meaning get rid of the fraction inside the fraction, but this is going to simplify quite a bit because e to the 0 is 1, but this is also e to the 0. This is 1 minus 1, which is 0, and it's over 2. Well, anything 0 over anything, that's not 0 because we know 0 over 0 is not that great anymore, but 0 over 2 is just 0 because this is just 0 on top. And on the bottom, what do we have? Well, it doesn't simplify quite like this, but it still simplifies a bit. E to the 0 is 1. E to the 0 again is another one. So 1 plus 1 is 2. Divided by 2 is 1. And we have 0 on top, not 0 on the bottom, which means this is 0. So hyperbolic tangent of 0 is 0. And you can check it. And in fact is 0. When you use Wolfram Alpha, if you just use that preview after a whole number, it always puts that little period, the decimal spot, but it's just 0. Right. But you could do any trig function like that, any of the hyperbolic trig functions. What's kind of funny is that when I was writing this next example, I was going to do hyperbolic secant, but I realized in what's called LaTeX, the way I write this, which is made for math specifically, you can't actually use hyperbolic secant, cosecant, or cotangent. And that's just something I was going to talk about when we get to the derivatives, but they're so rarely used that you pretty much never use them. It's usually just hyperbolic sine, cosine, and tangent. But if you did have to figure out hyperbolic secant at x equals 1, what do? Well, by definition, it's 1 over cosine, hyperbolic cosine at 1. And hyperbolic cosine, I guess that's the one we've done in all of them, so we probably have that formula down by now. It's e to the x, e to the 1, plus e to the negative x, e to the negative 1, over 2. And now, once you're here, since this is not going to simplify, at least as a whole number like some of the other ones did above, it's going to be more like number 4 here, or sorry, number 2 here. We just pretty much type this in the calculator. Now, depending on how comfortable with it, you could type this in the calculator right now, or you could do keep, change, flip, get it as a single fraction, and then type it in. If you do keep, change, flip, the top part is just the 1. We change the big old division bar here to multiplication, and we flip the bottom fraction. The 2 goes on the top, and e to the 1, which is just e, plus e to the negative 1. You could write it as e to the negative 1 or 1 over e. It's up to you on the bottom. But I always like simplifying as much as I reasonably can before using the calculator. That way I can be more confident that when I'm typing in the calculator, I'm less likely to make a mistake. But on the top here, we have 1 times 2, which is 2 over e plus e to the negative 1. And now this we have to use a calculator for. Go ahead and do that. We got 2 divided by e plus e raised to the negative 1. And rounded to 5 spots, you get 0.64805. 0.64805. If you want to press enter, just make sure it's reading it correctly. You can, and it is. So I'm going to go ahead and write down our answer here. 0.64805. And if you want, kind of use Wolfram Alpha, if you're working on your homework or the practice problems, go ahead and you can type in the hyperbolic secant, SCCH of 1, and you can see that it matches. So we did it correctly, but if you don't have a calculator that actually has this built into it, which I'm sure pretty much every calculator doesn't, make sure you're practicing it like this. Now, this is a good place to stop the first half. In the second half, we'll talk about the derivatives of the hyperbolic trig functions, and we'll actually see one word problem. So you know that we really do use these functions, especially the hyperbolic cosine function, in nature. I'll see you there.